class that you really care about that you feel should run well with ghost linkage, like say the dead code elimination. So you just internalize the last external function you care about. You can run DCE. It should clean up after you. It doesn't, because it doesn't know what ghost linkage is. So what do we do with our transformations? Well, again, we can take advantage of the fact that we probably don't need to optimize the runtime library that we're loading, since we probably optimized it when it was built. So here we can run internalize, dead code elimination, and inst combine just on the code that we generated from Clang and optimize that before we hand it off to the linker, so that we're just running our optimizations on a tiny little chunk of code, and we just assume that the runtime library was already linked. And the only things we have to run after link then are anything that would do IPO. So there would have been a demo here, but apparently my demos aren't working right now. So, and you would see it go like 20 times faster, because it's just that much more awesome. Literally square numbers are flying past the screen. And so basically, that's because we don't have to sit there and spend billions of cycles calculating the IR and reading off disk for all these things that we're just going to end up throwing away after we internalize and run dead code elimination. So, and not only that, because we didn't have to load all that into memory, we only use 3.9 megs, which is still a lot of memory, but it's way less than 31 megs. That's right. Nobody does that. So, if you had a substantially smaller library, if you were JITting from a known little chunk of IR, you could potentially get that down to 1.9 megs or something like that. And we are always looking for ways to crank down on the in-memory footprint of our IR, reduce the code size and the memory footprint of our transformation passes. So anyway, you may have additional questions that for whatever reason might not be answered here today. Here are two mailing lists you're probably interested in. The main LLVM mailing list and the Clang mailing list. And web archives of these lists are available, so you can go back and see what, how we've shamed ourselves in the past. All right, who has questions?
What about more dynamic compilation? Actually, first a quick question.
All right.
Is there a generally agreed upon definition of JIT? Does that only mean like literally, you don't try to interpret it first?
Well, I mean, to me, a JIT means anything where you didn't have the binary laying around on disk to begin with, ready to go execute. So, in this sense, we're taking it to mean we just in time turned it into executable x87 instructions. It could mean you just in time interpreted your Perl from the command line, or I mean, I don't think that JIT is a really well-defined term, but basically it means I didn't ship you a binary that then you clicked on and the operating system just ran without any intervention.
Okay, so what about dynamic stuff like, what if that square thing, you want to say interpret it until you find out, whoa, that's a hotspot.
Sure. So LLVM has two different things. The execution engine has an interpreter. Unfortunately, it's somewhat limited since it doesn't get a lot of love. It can't handle vector instructions, for instance. There's probably other things it can't handle. But you can run you can interpret LLVM until such time as you're ready to turn it into native machine code. Another thing you could do is you could say, don't do any optimization, just call CodeGen. And it will turn it into moderately gross native instructions, and you can run that. And you can layer your own profiling on top of that. You could put intrinsics in the IR, similar to doing gprof at runtime or other profiling tools. And I mean, you're creating the IR. So you could, create atomically incremented globals for every function you're generating, and then go read them at some later point and say, oh, okay, I want to go dig that function out of the library. Run the optimizer on that, and then tell the JIT, throw away the machine code you've got for that function and recreate it. And then, you'd spend your optimizing cycles on things that you actually knew were being running. For our test, for the demo today, clearly that didn't matter. It didn't even work. But, whatever.
What about taking that a step further and saying, hey, I've noticed that squares fall with 0 a lot. But sometimes it's not called with 0.
Right.
And I'll create 2 different versions.
Sure. So that's something, specialization, for instance. So that's actually really easy to do in the IR. Basically, what you say is create an empty function, call it x or whatever, or my square wrapper, and in my square wrapper say, if argument equals whatever, call this, else call square with 0, and then you say, hey inliner, go handle that for me, and it's going to actually just turn that into if the argument doesn't equal 0, call square, else return 0, and hand you back the code for that. So you can create, by creating sort of generalized IR with whatever things that you want, and then saying, hey, go JIT this for me, you can sort of get whatever behavior you want. You can.
What if you don't know a priority that that's going to happen?
Well, if you had a way of recording what the function arguments were, you could create a switch table of the hot ones and, at runtime later. But the JIT isn't going to go do that on its own. So.
What would happen if the square function had called other functions that you hadn't?
Okay, so if they were in your address space, the JIT would just find them. So if you called printf, for instance, or whatever, it would just work. If you called, malloc or free. If you have another library that contains helper routines that you want to call, you have to register that with the JIT. If you have, that would be a precompiled shared library of other symbols. So, you could use the load library functions with that. If you had other IR modules sitting around that you didn't care about doing IPO with, you can just add them as additional module providers to the JIT. And when it says, I don't know where the symbol is, it'll go walk the list of module providers saying, do you have this, do you have this, do you have this? If you do care about optimizing across those boundaries, then you do what we did here. You say, I'm going to link these guys together, run my IPO, and then it'll find the symbols because they're all in the same module.
When do those functions actually get JITted?
They get JITted on demand. So basically, when you JIT a function and it calls external stuff, the JIT rewrites a call back into the JIT for that set call and says, hey, if I ever hit this, go do that. There is a global flag that you can set that says do